Without further ado, Micah Miller on a primer of homotopy limits.
So thank you for inviting me. I'll be talking about homotopy limits, and I thought maybe before giving the general definition, just look at some examples in some simple cases. So if X is a topological space, and K is a simplicial set, I want to take the power x to the k. This will be a topological space. We're saying this will be the space of maps from the geometric realization of k into x. And so if we have a functor from a small category into topological spaces.
It's not, you use a different letter, X. X is a topological space.
Oh.
No.
So then the homotopy limit of f is going to be the equalizer so I'm going to take this product F alpha is my topological space, and then I can take the nerve of the over category over my object alpha. This is a simplicial set, so we're taking maps in the geometric realization of this into F, indexing it over all objects. So I need to define two maps into this product. Here we indexed over objects. Next we index over morphisms. Where it's pretty similar, except I'm changing, so we're going from nerve, the over category over alpha, into f of alpha prime. Okay, so I need to define two maps. Anyway, so if I have a map into f alpha, something on this side, and I have a morphism alpha to alpha prime, then I can look at the corresponding morphism from functors. I have f alpha to alpha prime, and that'll map me to a factor in there. Also, I map from alpha prime to alpha, and I have a map from alpha to alpha. I have a map from the nerves, and I just pull back, and we'll call that psi. And so we do this to every factor here. Then we take the equalizer.
Ordinary equalizer.
Ordinary equalizer.
So just for before you go, what would be the ordinary colimit of the limit,
Ordinary
limit of f? What would you change there? You would just put.
I think it would just be f alpha to f alpha prime. We won't be taking these powers. So the nerves here of these over categories, they're contractible. So this is sort of like a thickening.
Oh.
I'm sorry. I agree with that. I just say again. What's a thickening? Why is it a thickening? I mean, C is your diagram category, and you're looking at all things over A. And so, what's the nerve of it?
So f of something is now a topological space.
Right.
Yeah.
So that's a simplicial set, the nerve of that.
The nerve is, and it's also a contractible simplicial set. It has a terminal object, alpha over alpha, which is the identity. Yeah. So we can take a look at some simple examples.
Sorry, notation I missed. You have E down arrow alpha. What is the down arrow?
No, it's C.
C down arrow.
C.
Either way, slice. Oh, it's the
Yeah.
slice. Okay,
Yeah.
that's your slice notation. Okay.
Okay, so
Say, just sorry to interrupt again. Suppose F is not into top, but it goes into the homotopy category, or however you wish to define this. Homotopy. See, you're constructing a homotopy code, a limit, so, I mean, you should be able to do that for a homotopy diagram.
right.
Your diagram is in top, it's not in.
Right, so there are some more general ways to define a homotopy limit. I guess I'm not quite familiar with those.
Like, you know what I mean? It should,
Yes.
it should be, the diagram should be in the homotopy category. I want to know the limit of that.
Right.
Usually homotopy categories don't have limits that much because things are so not rigid.
But do they have homotopy limits?
Oh, I thought you were saying, do they have, should the homotopy limit be a limit
limit
in the
in the homotopy category, right.
Is that
And
true?
maybe nothing saying we don't know is.
Well, that doesn't matter, I don't mean that.
Okay.
I just mean.
There's some generalizations,
And
maybe I should look into it more, but
But even that.
I'll eventually define a homotopy limit in a simplicial model category.
Oh, yeah, okay.
That would be my setting.
Yeah.
The components of the space.
Okay, so this was our category C, just two objects, one morphism between them. We're calling this F now. We want to take the homotopy limit of F. Okay, so first, we want to take the nerve of the overcategory over A. But there's only one morphism on A, just the identity. Right, so it's just a single point. On B, we have two elements. We have A to B, and then we also have B to B. And there's a map between them, so we get an interval there. Okay, so let's take a look at our product then. We'll take f of A to nerve is C over A, but f of A is just x. Maybe I'll just denote it by a point, so it's just x, but we're taking maps of the point in. We do the same thing with y, but when we take the geometric realization of this one, we get a path. So we get paths in y. Right. Okay, now we do the same thing, but we're going to take the product indexed over morphisms. We have three morphisms, the identity on A, identity on B, and the map. So I don't know if the identity is really worth writing out. That's the identity on A. Identity on B. And then if we map, if we take the map from A to B, then we're taking y to the power nerve of the overcategory over A. So pretty simple. Okay, so let's take something in here. We get a point in x and a path in y. The identities don't really tell me anything. Okay, so now I want to get a point in y, and I want to use my functor somehow. So one thing we could do is look at morphism in top, and I can apply that to my element x. So that'll give me equivalence. So we call that phi. Or we can look at the map induced on the nerves of the over categories. So what happens there? So if I have, I want to get a map from here to here, induced by my map from A to B, and it's going to take this point here, and it's going to map it to that element there. I'm just going to take that composition there. So I map to the beginning of my interval here, and so we're taking our path, and we're just evaluating it at 0. And so if I'm taking the equalizer, I want these two things to be the same. So okay, so I have my spaces x and y. I have a point in x, a path in y. And I want my path to start at f of x. And I guess I learned this back because I learned the homotopy limit and then was told it's called the mapping path space. But I think this is something people study in other situations. And then you can show this.
But there's easier ways to get the mapping path space also, right? You can, it's just a pullback of something.
Yeah. Okay, so let's take.
Well, you can do this all night. This is very nice.
Okay.
This I understand.
Okay, so let's make something a little bit more interesting, but not that much more. We'll put in another element C. Suppose we had a composition of maps, so that gets mapped to. We get 3 spaces.
But we just do something with a bubble or a parenthesis, just so, because hiding those arrows makes it look like a huge sequence.
Yeah. Yeah. We're calling that F. Okay. Nerve category over A is still 1 point. Over B, it's still an interval. And then with C, we have 3 elements, A, B, and C, all over C. And we can map this out at B to C and this one to C. And then like before, when we want to look at the induced maps, A over A gets mapped to the first part here, and then this AB over B gets mapped to the first part.
The nerve of the third thing is a triangle or a path?
Well, so it's, yeah, it's a triangle, I think. If you,
The second
There's a pit.
is a
Dash.
simplex, and then over the third is two simplexes glued together, right? So along the B to C arrow.
okay, so we have, oh.
Oh, I see,
Yeah. We're mapping the curves.
yeah.
Okay, so again, we want to look at our product indexed over objects, and then we're going to map the product indexed over maps. So let's see, we have the identity over A, and then I want to look at identity on B. And then I have, so that gives me paths in Y, and then I get, F gives me points in Y. And then I have my Z, that's identity over C. I have paths in Z, that's given by G. Right, so we're going to look at the nerve of the category over B, and then map into Z. And then we have the composition, which will give us points in Z. So I have a point in X, I have a path in Y, and I don't know what notation, but maybe T for triangle in Z, mapping that in. Okay, so when we map it over, we can look at maps. We can look at the maps in top and induce the things there. Identity doesn't do anything, but then I can take F. That gives me a map from X to Y, so I can apply it to a point. I have identity on Z. Identity doesn't tell me anything. Now I want to get a path in Z. Well, I have a path in Y, and I have a map G. Wait, it's indexed by the G. So I can take composition. And then I want to get a point in Z. Well, I have a map from X to Z, and I have a point in X. So that. Okay. Instead of looking at the maps in top, we can look at the maps induced on the nerves. Okay, so I have
What's the
Oh.
right now?
yeah. Oh, yeah. Okay, so I want to get a point in Y, and I have a path, but since this map, again, goes to the beginning of that interval, you can take the identity doesn't do anything. Over here, so I have a map from the triangle into Z, and I want to get a map just from the first part, so I can just restrict my map to that edge. I'm not sure quite how to say that, but we're restricting to that edge then. Or we can restrict even more just to that initial point there. Okay, so we want to take the equalizer, which means we want to get everything where these two things are equal. Opposition, so okay, so I have a point in X. I can map it over by F. I also have a path in Y, and I require that my path starts at F of X. Then I have a map of a triangle into Z, and I want G of F of X to be that point, and I want this edge to be G of P. And the other things can, no restrictions there. Okay. So another example. Maybe we'll have something like this.
Does this have a regular name? What this equalizer would be? I mean, it's
Generalization of the last one.
no, definitely.
Yeah, I'm not sure. I haven't seen a name for it.
Mm.
It just sounds like that you have generalization will last into one more dimension.
Right.
Yeah.
Stick a 2 in front of it.
Yeah.
Okay, so we can take a look at something like this. This is still a point. Okay, so we have three objects here, because we had A over B, B over B. We also have a map C to B. And I have maps going this way. And then over C, it's just a point again. Okay. So, add up our product. So we have X. It's like we have a path here, but I don't know, 0 to 1/2 and then 1 to 1/2. Running into each other. And then we have Z to a point. See, I have identity on X, identity on Y. Then I have F, which gives me just points in Y. And then I also have G, which gives me points in Y. And I'm running out of space, but that's just the identity on Z. That won't give me anything. Okay, so I have a path. So I have a point X, a path in Y, and then Z. Okay, so identity doesn't give me anything identity on Y doesn't do anything, but with F, if we're looking at the maps in top, we can apply the map F to X. If I'm indexing by the map G, we'll have a map from Z to Y, so I can apply the map G of Z, and then I have the identity. And I'm running out of space. So that was looking at that map. Okay, if we look at the maps on the nerves, what we can do, we get, so the map from A to B sends, again, this to the beginning of my interval. So I take P of 0. The map from G, which goes CC to CB, that gives me a map on the endpoint of the interval. So I'm going to evaluate at 1.
The group do that as homotopy in space. Then you can do that in the space and then
Okay, we'll figure it out
give it
later.
to nothing.
Sure.
Hard for me to follow
No, no,
two people at
of course,
once.
that's just-
Where does the interval come from?
We'll figure
Is
it out.
that, is that from A or no, that's from that?
From B.
Okay.
It's sort of 2 intervals,
I'm saying, yeah, that's when you were saying the interval, and I'm like, it's
Yeah.
really sort of two.
Yeah.
but I'm just, reparameterizing.
Okay.
Okay, so then what does this look like? So we have a point in X, point in Z. We map to Y, so I have an F of X, and I have a G of Z, and then I have a path between them. And we can take a look at a special case of this.
This is a good example, though, right, where we could look at the non-homotopy version and say, well, the homotopy version is really that you've taken two things that were on the nose and connected them by a path, and that's the homotopy version stretches out the original,
Yeah.
right?
But it's not homotopy class of paths in it? Or between
Mm,
F of X and G of Z there? So if you
No.
had a different path, but homotopic,
It would be a
would
different
be a
thing in
different element in the homotopy
limit, yeah.
limit? Pull that?
But then all those things would be the same up to homotopy, right? So that's sort of, even if they're different things, you can, under homotopy.
No, but there are two different elements, he says, in the,
In the homotopy, yeah. In homotopy limit, we're not saying take equivalence class.
Right, but
Because
I'm
he's
saying, but
working-
then,
right, he's working
then if you
out,
look at
yeah,
that object
explosion
up to
that-
homotopy, then you
Yeah.
can't tell them apart again, right? Because,
Unless we had,
Well, the space might have lots of
Unless-
holes in it.
unless it's,
And there might
not
be-
unless it's simply connected.
okay, I see, yeah.
Well, I'm probably misunderstanding everything because I came in late and I'm stupid. What more would you have to add to your span or cospan, I forgot which is which, in order to force non-trivial homotopy in the lower right corner? What would you have to add? What would you have to add to the diagram? What extra information in order to force non-trivial homotopy? In other words, you have to make an official list of the paths.
Okay. We'll make that.
So we're saying an element here is f of x, g of z, and a path, a choice of path.
Yeah. Oh, then I.
So-
Yeah, that's what John's saying.
Yeah, we're not
It's
taking.
just an element.
You have no notion of
That's not what we
homotopy
say,
yet.
okay. Okay.
I'm sorry, okay, so now
Non-homotopy paths gives you different elements.
Yeah.
Homotopy paths give you
Right.
the same element.
Yeah, of course.
That's all I'm saying.
Yes.
Okay, suppose we had this, this map. We're taking the diagonal map of x into x cross x both ways.
Let's say with Gersham's thing, you can understand now what you did the first one. You like usually the co-limit of the limit of a map is just
First thing.
the first example. Okay, so you thicken it up, so that makes sense. Okay, fine.
Yeah.
All right, good.
Well, in particular, the first two, the ordinary thing would have been trivial. The limit would just be take the first thing. But here it's a non-trivial thing.
But also I'm saying that if you were to take fundamental groups of all four things, you know, of the square, that's a homotopy pullback of groups. You know what I mean? It's not going to be a group pullback, but it's a homotopy. Say if you take.
Right, if you look at
Or
fundamental
apply-
groups,
apply
because then
pi
you're
1 to that.
secretly doing topology.
So yeah, so that's what we want to do these homotopy colimits of groups without doing.
That was what I was
I
getting
see
at.
what you're getting at.
Realize your group as a,
Yeah.
yes, a homotopy of a space, then you
But
can
then you have
do
to,
this.
You know,
yeah, you
skip
have
it.
to.
Do it independently of topology, just algebraic.
Sure.
But it should coincide with the
Mhm.
fundamental group in this way.
Yeah.
But anyway,
Okay. So suppose we were looking at the diagonal map into x cross x both ways.
yeah, that's interesting. Yeah,
So I have a point x in x, a path in x cross x, and another point in x, and we're sending it across. Let's see, it was x. The diagonal map is just xx. I think I ran out of space there, but maybe I put it here. We just have the
X prime.
doesn't matter. Or I have x, p. I do p of 0, p of 1, x prime. So let's take a look at what that is. So I have x and x, and I have my diagonal. I have 2 points on the diagonal, x comma x, and x prime comma x prime. And I want a path between them. Okay? But a path between them, I get one path from x to x prime and another path from x to x prime. And so I can reverse one of the paths, and I get that the homotopy limit in this case is the free loop space.
That's nice.
that's pretty
That's
good.
really nice, yeah.
Yeah, that happens in group actions too, by the
Okay.
way.
Yeah, so
Never mind, but I'll show you.
maybe I have another, so I have one more example, I guess, that I was planning on doing. So let X be a G space. I want to think of this as a functor, so we can think of G as a category
Okay.
with one object, and morphisms are the group elements. And then I can think of my G space as defining a functor from the category G into pi. Okay, well, we could just take the limit of x, right? And what would the limit be in this case? Right.
Just a stabilizer, I guess, or something. Yeah.
It's the fixed point set.
Fixed points, yeah.
Right, so I have all these maps, all these arrows, one for each. And I want the limit to map to all these things so that the diagrams commute. So I can take the limit of x to be the fixed point set, just included into G. And that'll be the limit. So then what's the homotopy limit? You want to take time to think about it, or? Okay, so the claim is that the homotopy limit is the homotopy fixed point set. Of the G action. So the homotopy fixed point set these are the G equivariant maps from EG to X. So EG is a contractible space with a free G action. As a G action, we can ask for the G equivariant. Okay, so
So
let's
you're
see.
taking the, right, so you're taking the point of that contractible space.
How is BG related to that?
So EG mod BG. I mean, EG mod the action will give you BG.
Right, so it's not that.
EG over BG is the classifying, or the universal bundle.
Yeah, right.
So, yeah, let me double down on asking the basic question. Now that someone wrote dice, so I know what a PG space is, or I think I do.
Yeah.
So what is just PG definitionally?
So you can define just a contractible space with a free G action.
Okay.
So it's-
they would say, is that the EM space or something? Is that, or no, was
Well,
that different?
because that's defined that way too.
Yeah.
K pi 1, KG 1.
So it's the Eilenberg-MacLane space of the group.
Yeah, because all you have is the group. because
Well,
once you take
EG is the
group,
total
right.
space of that.
Right.
It's contractible, so.
Okay.
Okay, but maybe, yeah, it should come out. Let's take a look. So, so we're looking at the nerve of G over the point. That's our only element. Oh, and let me say, I think it should be true if for any group, but let's say G is just a discrete group. There's some. Let's write that. Okay, so this is the thing we want to equalize, this diagram here. Let's take a look. So the over categories, again, is going to be G again, but it's going to be represented differently, right? It's going to be category where the objects are the group elements. And the morphisms, so there's a unique morphism between any two. And then, yeah, that's just sort of definition there. Okay, so let's take a look at the nerve as a simplicial set. So in degree 0, those are just the vertices here, so that's just G. Over here, 2 elements I get unique elements. So in degree 1, I have G cross G. And we get, so this is simplicial set, so we should get 2 maps from 1 to 0. And just definition of the nerve, we get 1, a projection onto one of the factors. That's one map, and the other map is the group multiplication. This is the definition. And then in degree 2, we have G cross G cross G. We have 3 maps, and again, it's the same type of map we're going to define this way. We can either project or multiply 2 consecutive ones. And we continue in this way. And this is actually the definition of EG as a simplicial set. If you take a look, so I think basically we have it now then. I was thinking about this afternoon. I didn't have the statement quite clear before. Now that it's worked out, I think it should just fall in place. So we have, so if we're taking this, just remember to take the simplicial set. We're looking at maps from the geometric realization. Into X. But what we showed there is that the geometric realization here, that nerve is just EG, and we're mapping into X. Here we're looking at just any map into X. Not necessarily G equivariant, but when we take the equalizer, let's just take a look at what that says. So one map is, I take my map, so I send my element over to X, and then I apply the G action. I think I was calling that map phi. If we map on the nerves, that means we have our map, but we apply the group action on EG first, and then map it over to X. And so the equalizer says we want those 2 things to be the same. Definition to be G equivariant.
Very nice.
And I think the discrete group comes in just, you can take the sort of the naive topology on this to get a space out of it. If it's not discrete, you have to give some other topology. I forget the details, but.
So this has nothing to do with top practical, right? The construction you've just done. It could be basically any category almost.
Well, we need a model category.
So I need to be able to define my object to a simplicial set power.
Okay, thank you.
Define that.
Thank you. Sure.
So maybe now is the time to give the general definition. So these were just a bunch of examples, and we did it really minimally, just the one thing we needed in top to calculate these homotopy limits. Okay, so for the general definition, we need M to be a simplicial model category. Okay, so that means, in particular, M is a model category. So we have our weak equivalence fibrations and cofibrations with the axioms. It's also a simplicial category, which means that for any two elements x and y in M, map xy is a simplicial set.
So it's enriched in this.
Yeah. I have the compositions that satisfy the associativity conditions and the identity being the unit. And I want my simplicial set in degree 0 to be my
Let me ask you a pain in the ass question. If you have a simplicial category, then doesn't that, well, I guess the problem is it might come with more than one, but doesn't that automatically come with at least one model structure on it? Or at least two?
At least two.
You mean coming from the model structure on
Yeah, I mean,
simplicial
yeah,
sets?
on S sets, yeah. So it's the point is that you could have more than one, but if you're in a simplicial category, you always have at least one model structure, right? I don't know. I'm asking. I think so.
I actually haven't thought of that.
Okay.
There's another thing also, that every model category can be embedded into a simplicial two category or something, or into a simplicial category, even without that. No, there's something.
Oh, actually, let me. Yeah, I'm not sure, but a simplicial model category is going to have two more axioms.
Okay, I see.
So it's not just
Yeah.
And so. Okay, plus, so if K is a simplicial set, x to the k and x tensor k are also elements in our category, satisfying some axioms. Let me just look at my notes for that.
What does that mean, the tensor?
Yeah, what's the tensor?
X tensor K?
So it's, again, it's part of the structure.
Part of the
So
definition.
part of the definition. This is, so if you want to show something's a
Understood.
simplicial model structure, you have to define these. But it has to satisfy sort of a tensor axiom. So okay, so K and map XY are both simplicial sets, so I can look at the and simplicial sets.
Right.
And then I also have X tensor K. So it's something in my model category. Y is also in my model category. Map is defined, that's a simplicial set. What I think is in there. And then we also want also that powering.
Is that your, what, simplicial set notation?
Set delta, yeah.
Okay.
What is this called?
It's a simplicial model category.
No, what is, but I mean, the axiom you just wrote down, what is that called in case the things were just sets? Is that Cartesian closed or something close to it?
This is sort of like the Hom tensor adjunction.
Okay.
Yeah, it looks
Yeah,
like
which-
Cartesian
yeah.
closed.
Okay.
Which is-
Okay,
Okay, that's good.
yeah, thanks. Okay, I want to make sure I was, more an issue of my eyes being clear.
Is there a naturality condition?
And then there's another, yeah, so if so if I from A to B is a cofibration,
Yeah, power over. Absolutely.
so if we have a fibration and a cofibration,
Here it comes.
then the map of simplicial sets let me just is a fibration that is a trivial fibration if either I or P is a weak equivalence. I'm not quite sure what to say about this. The Hom tensor is sort of right, but yeah. So this is a simplicial model category. Top is a simplicial model category. So I mentioned this earlier, that the powering as from the geometric realization, the tensor is Cartesian product with the geometric realization. And so, and then map x, y, we want that to be a simplicial set, so in degree n, we're saying that's Hom of x cross delta n into y. And then you use your phase and degeneracy maps. Just on that. So this, with the usual model structure, will make top into a simplicial model category. Simplicial set is also is a simplicial model category. Yeah, it's pretty similar, I guess. Tensoring is just Cartesian product of simplicial sets. Maybe I should have defined map before. Okay, so map between two simplicial sets. And in degree n, you're going to take the Cartesian product. With delta n.
I think that's just the ordinary exponential in the topos of simplicial sets. Anyway, yeah, it's just the...
Okay, yeah.
Yeah, it's self-indexed, so
It's just the, well, anyway.
there any restriction on top? Doesn't top have to be nice topological spaces? I mean, if they're going to be, if they're going to satisfy that,
MLab says compactly generated.
Well, that's
I don't know
usually
if
what,
that's.
well, that's usually what everyone uses in algebra.
I don't have that, yeah, maybe. I guess I should check.
Sort of the standard running assumption in the subject.
Okay, so with this, we can define so if we have a diagram in a simplicial model category, the homotopy limit, it's the equalizer, what I wrote before, but now it's defined even if it's not top. So home limit is the equalizer. We take the Cartesian product over the objects. Nerve, again, is a simplicial set. Since this is a simplicial model category, this is defined. We're taking two maps over. We're taking the Cartesian product indexed over morphisms. Yeah.
We interpret what it means to raise x to a simplicial, to a
Yeah.
to a complex.
We didn't use tensoring, but for tensoring you need to define the homotopy colimit. Maybe I'll write that down. So the homotopy colimit is the co-equalizer. And so it's going in the opposite way. So we're taking disjoint union and we're first indexing over morphisms. We have X alpha tensor nerve of the. I've been mixing up over category and under category. I think it's the category under alpha.
Everything's reversed.
Yeah. Yeah, sort of.
So point being, yes, the dual to take exponential is now the tensor product.
Yeah.
well, what's the purpose of the op? Is that op and top?
Yeah. I think it's to get some different compatibilities between the homotopy limit and colimit. So the adjunction conditions.
So I guess one thing I was going to ask, now you wrote it down, I was wondering with your simple examples, what would be a or maybe you're going to get to that. Geometry of the colimit.
Of a colimit.
Which one of these simple categories works?
I haven't really. I think the colimit is supposed to be more geometric, but I actually haven't worked out examples.
Yeah, I was thinking like, let's say, I mean, not
maybe
in
one thing I
time,
could
but
have-
something like the, even take the stupidest, thing with the 1 hour or whatever and whatnot.
But the motivation, why take homotopy colimits in the first place? So we can take colimit of this diagram. Right, so we're mapping to the boundary,
So that's the disk
and then the
sphere.
disk.
Yeah.
So you get the sphere. Then you can also take the homotopy limit of this the colimit of this diagram.
This is regular colimit, not homotopy.
Regular colimit, yes.
Yeah.
And that's just the point. But dn is contractible, so we have equivalences here. And so we have a map from the colimit of this diagram to the colimit of this diagram, but it's not a weak equivalence.
Right, clearly. Otherwise, a lot of jobs would go away.
Yeah.
I see, where's the homotopy limit? They no
They
longer
use math
coincide.
with
You can tell them apart.
Yeah.
I'm sorry, state that again. Where is the homotopy colimit? What would be the homotopy colimit?
No, so I think the homotopy colimit, so I think it's homotopy colimit, we should get a weak equivalence then. So then the homotopy colimit of this thing would just...
Well, because there you're gonna basically take your star point and replace that with a big enough contractible space.
Yeah.
Like Euclidean space or whatever, and then you actually get a, non-trivial thing.
Yeah.
Right. Yeah. Oh, no, in fact, sorry, I could be well be wrong. The bottom guy, when you take the HOCO limb,
Yeah.
right, that's basically just suspension, right? So
Yeah, that's how I remember.
so it'll give you SN as you desire. Right. And in fact, that's one motivation is it's a way to define suspension.
That's right. You basically that's right. You basically thicken up each of those stars to an n-dimensional disk, and then you see if you glue them together. Yeah.
I remember there was an example, maybe I thought I was just going to briefly mention, and then I skipped it. But I thought maybe your comments earlier sort of alluded to this. So we talked about G acting on a space, but suppose we had a representation, so it was acting on a vector space. So if we had a representation, I haven't worked this example out, so I think I'm just going to state it. I think it should be analogous to the homotopy fixed point set, but if you take, so you think of this as a functor from G to vect, but you want a notion of homotopy, so you're going to think of vector spaces as chain complexes concentrated in degree 0. And then I think if you take the homotopy limit, because I was calling of this thing, you get group cohomology. Or the chain complex that everyone defines to get group cohomology. And I think the process is pretty similar to the case with spaces and getting the homotopy fixed point set. Mahmoud was telling me this morning, and it seemed pretty convincing, but it didn't work things. Another thing he said was that if you take homotopy limits, or you can describe just about any cochain complex as a homotopy limit. And then homotopy colimits would give you chain complexes. Okay. Right, so the issue with trying to compute these homotopy limits and colimits is these nerves get pretty big. So it could get a little unwieldy. So let's look at maybe a special case. We have a suppose we have a cosimplicial object. In our simplicial model category. So we're going from delta to n. So the totalization is going to be the equalizer. And we're going to take a similar looking thing. We're going to, again, take the product over our objects, but the objects are just the finite ordinals, right? So we can take xn, and instead of just taking the nerve, we're just taking the standard n simplex. That's still a simplicial set. Put that in. And then for every map, we get a factor like this.
So that's the homotopy limit, not the colimit.
This is the totalization.
I know, but it mimics the homotopy.
It mimics the homotopy limit.
Right. Okay. Yeah. Is that your word, totalization?
No, that's in the literature.
Yes, then. Yeah.
Okay. And we can define a map from the totalization to the homotopy limit. To do that, we can define the Dwyer-Kan map. I was going to do it. So this is going to be a map of cosimplicial sets. It's going to go from nerve at the over category, blank, into delta. So let me say. So if we have a simplicial, so delta n is a simplicial set, and then if we take the collection of all these things, we'll get a cosimplicial object. So we'll get a cosimplicial set. And then same thing with the nerve. So for fixed n, we get a simplicial set. collection of all these sort of blank, we'll get a cosimplicial simplicial set. And so we want to define a map of these things. Okay, so for fixed n, I want to define a map of simplicial sets. Okay, so I want to map k simplices in here to k simplices in there. So a k simplex in my nerve is something of the form so we get composable maps. That's just in the nerve, that would be just in the delta category, but I want to be over n, so I also have to have a map so if I have a map for my last guy into k, then I'll have a map, all these elements would be over k. And then I want to map to a k simplex here. And so we're going to take these maps yeah, so these give me maps. I'm over n. I'm taking a k simplex. Change. So yeah, I'm mapping into n. So this is my Bausfield-Kan map. And this induces a map. So this went from the nerve to the standard simplex, or standard cosimplicial simplex. And so the induced map is going to go the opposite way. We're sort of pulling back our maps. Yeah. Okay, so let's see how that works. Okay.
How are we to think of, how are we to think of this Dwyer-Kan map? Is it like spreading out something, or is it the other way around? Is it compressing something? In other words, should we
Yeah.
think of tot of x as more rigid?
Yeah.
And it's including into the whole limit?
Yeah. Yeah. Totalization is more rigid. The induced maps between two totalizations might not preserve weak equivalences. It doesn't have nice homotopy theoretic properties. In special cases, the Dwyer-Kan map, or this, is a weak equivalence. Okay. So let me just state that, I guess. So if x, and we haven't defined this, the Reedy model structure, but I think it'll just take too much time. But if x is a Reedy fibrant cosimplicial simplicial object in M, then the Dwyer-Kan map is a natural weak equivalence. Okay, so I don't think we'd have time to go through all the definitions, but Reedy category. If C is a Reedy category, so just think delta or delta up, those categories. C diagrams in M can be given a simplicial model category structure.
Two. Two of them.
If there's two, if M is cofibrantly generated. Okay. Oh, and actually, if M is, M in this case just has to be a model category. It doesn't have to be a simplicial model category. And so then you can define homotopy limits and co-limits in this case.
Using this PK map.
No, why did I say this? Oh, so this does have a Reedy model category structure, and then so I guess I just said that. Okay, so Reedy fibrant goes. So Reedy fibrant means so it's a fibrant object with this model structure, which I didn't.
But I see. No, what I was asking is, you were saying, in this setting where you're not necessarily a simplicial model category, you can define, say, homotopy limits and co-limits. My question was, Do you do that via that BK map where you take the totalization?
No.
Okay.
No. So the BK map is just gives you another way to possibly compute homotopy limit in a simpler setting. So if it's a weak equivalence, totalization is usually easier to take the equalizer because the powering is smaller.
Okay. So the left and the right things there are independent points. That's what I was. Okay.
Yeah.
Didn't realize.
Okay. I think this might be a good place to stop.
Limits are built out of equalizers and products. Is there the same thing for homotopy limits?
Well, that's kind of how we define them.
You can define homotopy limits. You got homotopy products. You can find homotopy.
Homotopy product is a product.
Right.
Is that right?
Because it has no maps. And homotopy equalizers is not an equalizer.
We define the homotopy limit to be an equalizer
Of products.
Yeah. And what's the question?
The way I would state it is, if you want, you can say a category has all limits by showing that, well, it has, like 3 different types of basic limits, and then there's a construction that shows how you can glue them together to get every other limit.
Yeah.
Okay.
So is there a similar thing for homotopy limits, where if I show that you have homotopy equalizers, homotopy pushouts, or whatever, then that suffices to get all homotopy limits?
Well, we're in a model category.
So
we're taking the
you definitely
equalizers.
have all home. So I think that's the answer is, in the setting where you can define them, you have them all definitionally?
Yeah.
That's correct.
Right, well, I guess or you could ask, if you have them all, can I factor a homotopy
Less
limit
interesting.
into more basic limits?
Yes. Less interesting if you have them.
Sure. Well, no, but you want to prove this thing about all of them,
Yeah.
then you have to prove that about the basic ones.
Yeah, I'm not sure about that.
Plus, but of course, as your first example showed, even where the regular limit is trivial, the homotopy limit may not be.
Yeah.
Any other questions?
I thank you for this, and what you left us with was interesting. So at whatever time next year, however much, whatever, I think it would be interesting to just have a talk on sort of 3D structures in general, because as you said, it takes a while to state and understand the definitions, and a nice talk from you on that would be
Sure. And I tried to sort of avoid. I tried to give a bunch of examples.
Right, or just
right now, I could give the definitions, but not much.
No, but
What
also,
I was saying
also,
is maybe sometime next year you'd like to tell us just a little about 3D stuff, and not even co-limits or whatever, but just how to
right,
think
but
about
even
them.
even just more basic, yes, what does mean a model structure, and give the intuition behind it, not just here we wrote down the definition, but why do this?
Right.
You gave that big long definition, and is that available? You have that formal definition written up, and so it's, okay.
Yeah, I do. And it's written out, so most of this is from Hirschhorn's book.
Okay. That definition appears in.
Yes.
Ah, thank you.
Anyways, I think we should thank you.